Hello everyone, my name is Matchima Buddhanoy. I am a first year student, PhD student from University of Alabama in Huntsville. Today I will be presenting instant data sanitization on multiple level cell NAND flash memory. These are the topics that I will go over today. I will talk about motivation, challenge, background, and I will go over data sanitization method, evaluation of the proposed method, distribution effects, go over conclusion and future work. The main motivation for this work is that standard sanitization methods are insufficient. According to the article in 2019, 42% of used SSD and HDD sold on eBay contain the previous owner data, even though every seller properly performed data sanitization. Since destroying your data in electrical way is not a solution, some people decided to go with a physical way. Therefore, the standard data sanitization methods are insufficient and do not ensure true data deletion. That is our main motivation for this work. In NAND flash memory, a standard way for data sanitization is to unlink physical page address. If you can see here, the data still remain in the flash page, but the page address is unlinked. This is not a secure way to delete the data. The better way, more secure, is to overwrite with all zero. So you overwrite your current data sets with all zero data pattern. That is the better way to go about it for the data sanitization. In SLC storage, all zero overwrite operation can be done with no issue, no problems. But when it comes down to MLC storage, all zero overwrite operation will become an issue because MLC storage has share page. So the main challenge for this work for us is to sanitize a page without affecting share page of the MLC memory. In this work, we propose a solution. We propose an instant data sanitization method for MLC flash memory. Our method can reduce hefty overhead, leave no trace of the original data, has minimal impact on the corresponding share page, and require no hardware modification. Let me go over the background of flash memory real quick. NAND flash memory cell, it's essentially a floating gate MOSFET transistor. This is erased flash cell represent logic 1. This is a program flash cell represent logic 0. How do I know that the cell is in the program state? Because they are electrons stored in the floating gates. Cells in the same columns are connected together through bit line. Cells in the same row are connected together through word line, and that form a flash page. Erase operation can be done in the block level, while program and read operation can be done in a page level. Block erase is infrequently used because of the performance and reliability concern. Since we all know that flash memory has limited lifetime, the more PE cycle we perform into the flash memory, the closer we get to the end of flash memory, the lifetime of flash memory. So we don't want to perform the block erase operation that often. This is the distribution, threshold voltage distribution of MLC flash memory. Gray code is used to encode the states. L0 represent 1, 1, L1 represent 0, 1, L2 represent 0, 0, and L3 represent 1, 0. Blue color here represent LSB bits. Red color here represent the MSB bits. LSB bits from all of the cell states will form LSB page. MSB bits from all of the cell states will form MSB page. Before the MSB page get programmed, the LSB page will get programmed first. If you look at the here, the top distribution, it's the erased state of the flash cells. When we start programming, the LSB page will get programmed first, and then MSB page will get programmed later on. This is the simplified flash-based storage system. The system consists of controller and NAND flash chip. Controller will basically set command to flash chip, and flash chip will just either send or receive data to controller or from controller. This is more detail of system view. Flash translation layer is the interface. FTL is the provide interface between the host file system and the raw flash chips by mapping logical address with the physical address to the physical address, and the FTL will be in the controller. Our proposed sanitization method can be implemented in the FTL without any privilege command. So our method will be inside the FTL. Next, I will go over the proposed data sanitization method. The main goal for our data sanitization method is to sanitize a page without affecting the valid data on the share page. Let's say I program random data on both LSB and MSB page. This will give are equally distributed in the states. As you can see here, L0, L1, L2, and L3 are equally distributed. And again, as I mentioned earlier, blue here represent the LSB bits, red color represent the MSB bits. The first option is LSB sanitization because it's easy. To sanitize the LSB page, we would just need to move L0 to L3 and L1 to L2. If we take a look at the logic, excuse me, if we take a look at the logic, we can see that from L0 to L3, the MSB logic remain the same, which is 1. However, the LSB bits logic will flip from 1 to 0. Similarly, from L1 to L2, LSB bits remain, MSB bit remains 0. LSB bits flip from 1 to 0. Therefore, after LSB sanitization, we will get MSB data will remain the same. LSB will become all 0, as you can see on the logic. MSB sanitization is another option. This one is a little bit tricky because MLC storage use gray coding, meaning that we cannot move L3 to L2. Because in flash memory, we are allowed to move distribution up only. To move the distribution down, we have to perform erase operation, and that will move all L1, L2, and L3 states back to L0. So we don't want that. For our MSB sanitization method, what we can do is we can move L0 to L1 and move L2 to L3. For L0 to L1, you can see that the LSB bit remain the same, but the MSB bits flip from 1 to 0. In L2 to L3, LSB bits remain the same, but the MSB bit flip from 0 to 1. Therefore, after MSB sanitization, LSB data will remain the same, but the MSB data will be inverted of the LSB data. The next option is sanitize both LSB and MSB page. This is easy. You want to get rid of both two images without perform erase operation. What we can do is we just move L0, L1, and L2 to L3. And according to, if you zoom in and take a look at the logic, your LSB page will become R0 and MSB page will become R1. And this is the core idea of our proposed method. Implementation of LSB sanitization. There are two steps of LSB sanitization implementation. First, we read MSB page and store it in the buffer. And then we send the write command with R0 data on LSB page and buffer data on MSB page. The overheads include time needed for one MSB page read, set data to both pages, and program data into the memory cells. These overhead time, the overhead magnitude of the overhead in this process is still lower than the magnitude of the overhead that you have to, when you have to copy multiple valid pages to a new block. Our proposed method come with the smaller magnitude of the overhead time. Implementation on MSB sanitization. First, we will read LSB page and store it into the buffer. Then we send write commands with the buffer value on LSB page and then invert the buffer value on MSB page. Overhead includes time needed for one LSB page read, sending data for the MSB page and program data into the memory cells. And again, the magnitude of overhead times here are not significantly higher than overhead of copying multiple valid pages to a new block. Next is implementation of both implementation of both LSB and MSB sanitization. This one is easy. We don't need to read anything on MSB or LSB page. The only thing we have to do is send a command, send a page write command with R0 data on LSB page and R1 data on MSB page. So after we send this command, L0, L1, and L2 states will be moved to L3. Compared to LSB only and MSB only sanitization, this option, both LSB and MSB sanitization method, give us smaller overhead. And again, all of these sanitization options can be done without any privilege command. Next, we evaluate the proposed sanitization method. We use real iStyle image, program iStyle image on LSB page, and program Mona Lisa image on MSB page. Before sanitization, BER bit error rates are almost zero, close to zero. And after LSB sanitization, LSB page become all dark. MSB page, which has Mona Lisa, still have Mona Lisa, but the BER slightly increased. For the MSB sanitization, after sanitize the MSB page, iStyle image remain the same in the LSB page. BER also remain close to zero. However, the MSB page value will become inverted image of the LSB page. For both LSB and MSB page sanitization, after sanitize both LSB and MSB pages, Mona Lisa and iStyle image are gone, and BERs are 0%. Therefore, we conclude that there's no significant change in BER after sanitization method. We also done more experimental evaluation on multiple flash chips. We done experiment on 64-layer 3D NANDs and 19 nanometer 2D NANDs. And this is the top distribution is the experimental measured distribution, and the bottom distribution is our theoretical expectation distribution. If you can see here that this is just for LSB only sanitization. After sanitization, L0 moves to L3 and L1 moves to L2. Therefore, the experimental results align with the theoretical expectation. We perform experimental evaluation on retention effects after sanitization. Here we perform experiment on 3D NAND. We have a valid data on both LSB and MSB page before and after sanitization. We bake the chip at 120 degrees Celsius for 3 hours. 3 hours of bake time is equivalent to 5 years of data retention at room temperature. Based on our experimental results, we find that retention reliability of LSB page improve after corresponding MSB page sanitization, which is the blue color here. Why? Because after MSB sanitization, the margin between two states become wider. If you can see here in L1 and L3, the margins are wider. That's why BER's bit error rate improve. On the other hand, retention reliability of MSB page degrades after corresponding LSB page sanitization. Because the after LSB page sanitization, the margin between two distributions becomes smaller. Even though average BER increase after bake, the average BER still low enough that error correction code can correct it. Next, we perform experimental evaluation on the sanitization effects on the other memory layers. Here we have a average BER versus number of sanitized page on a given layer. The green line is the nearest neighboring layer. The pink line is the further neighboring layer. This experiment is done on 3D NAND. If you can see here, as the number of sanitized page on a given layer is increasing, the nearest neighboring layer BER increase significantly, while the further neighboring layer BERs remain almost the same. Even though average BER increased significantly, the average BER, the bit error rate still low enough that error collection can collect it. Therefore, we conclude that sanitization process slightly impact data integrity in the neighboring pages, but still can be corrected using ECC. There are some limitations on this work. First, in some NAND flash memory comes with internal data randomizer, and that will prevent overwrite-based sanitization. Second is that some NAND flash chips have no overwriting support once a block is fully programmed. In conclusion, we propose an instant page sanitization method for MLC flash memory. The proposed method comes with minimal impacts on corresponding share page. No effects on memory endurance because we did not use block erase operation. Does not reduce the available memory space. Can be implemented within the standard FTL with minimal firmware change. For the future work, we'd like to expand this work to the triple level cells. We also would like to explore more on the original data recoverability And we also like to examine on the age blocks because most of the experiment we done here in this work, it's on the flash blocks. And we also want to explore more on the subpage sanitization where half of the image gets sanitized. And thank you.